Hey, what's up, YouTube? So here we are back again, the HVAC Optimal Start Math Playground. So we're studying mechanical engineering theory here for optimizing how long it takes to start an HVAC system before the building is occupied to condition the zones. We're going off of this research paper, so it's a good read. It's in the on the repo, which I'll link in the notes. Yeah, check it out. PNNL, they put out a lot of good stuff. So I've been studying this pretty hard for about this entire 2025 and implementing it in the real building automation system in the Niagara framework in Java, but we're just studying it here in Python in pseudocode format. So okay, so we've talked about this paper a few times. Resistance capacitance model, kind of like upper graduate mechanical engineering theory, which I do not have, but learning a ton here with our AI generated coursework. So we have all these variables that's in the paper that we're trying to replicate in Python. And okay, so now we're getting into the more complicated models. So model 1, which we did already, model 2, which we did already. Model 1 was the quadratic representation of the difference between the occupied zone set point and the zone temperature before the zone is occupied. Zone temps drift. So this is a quadratic regression, and we solve for alpha A and alpha B parameters. Becomes a self-tuning model. Model 2, which was our last week, this one was a degree per minute model. So this was just linear degrees per minute. So if you would actually calculate the zone, how long it takes to condition the zone in degrees per minute, linear fashion, it was taking that as and then multiplying it by a ratio defined by the outside air temperature. So it was the outside air temperature previous minus today, and basically you calculate your model calculates minutes based out of that. So we have that. This is the one I'm actually testing out, and we were talking a little bit about yesterday. Pretty simple stuff here. We were talking a little bit about all of these models are relatively simple, I think. Like there's not like a lot of data. Like this model takes 14 days of data. So in the Niagara program object, I'm just sampling live values. In 14 days of data gets saved to an array, which is just a representation of the, where are we here? So this is just like our math equation just gets saved as an array. And we have 14 days of performance data, so that would be basically the how long it took to condition the zone in minutes and the zone temperature at start in minutes. So 14 days of data, and we run it through our regression equation that we solve. Same thing with here. There's actually no data that gets saved, because like every time that the model updates, that we update our tuning parameters with the closed form mathematics. So there's no saved data. So relatively simple stuff. It's not like machine learning, or doing something really complicated where an enormous amount of data is getting, from a database and, running all these different tests, this is relatively pretty simple stuff that runs well, I think, on the resource constraint devices, like a Jace in Niagara World. Okay, so we're getting into Model 3, which is relatively a little bit fancier math. To do this one, it was requires some linear algebra or matrix algebra and multiple regression. So we're getting into this. This model takes account in outside air temperature as well, and like we solve for 3 different alpha parameters again. So this model, it gets actually a little bit too complicated for the Niagara program object that I'm using, because there's no linear algebra libraries to do matrix algebra calculations. Which we talked about yesterday, I'm only doing model 1 and 2 in the Niagara world and comparing the average squared error. So models 3 and 4 that we'll getting into, this is too complicated for my building automation framework, because we don't have any math libraries to play around with to do fancier math. But it's not an enormous amount of data that gets trained for like a machine learning model or anything. It's just the same thing as Model 1. It's just 14 days of data that'll get saved in terms of performance history. So it would just be the temperature that it took to this delta temperature here. So that's the set point, the occupied zone set point, and then the temperature that we ran the optimal start algorithm. So that difference, if the zone in where I'm at right now, like it's cold in the wintertime, so if the zone sinks below set point 8 degrees and we have to warm it up, that's this temperature difference. And there's also an outside air temperature that will record at that same time, and the amount of minutes. So then we'll run some fancy multiple linear regression across that, and we'll ultimately output minutes. And this was in the paper they talked about, this model had the best performance out of all the other models, but not by much. And I think the next runner-up was this Model 1, which is great for maybe interior zones of the building where it doesn't have a huge effect on changes of outside air temperature. But if there's an exterior zone, I think this Model 3 has, by the research study, showed the best performance. Okay, so let's get into it in Python. Maybe actually we should jump to our math lesson. So this paper is stored here in the PNNL paper section of the GitHub repo. So I'm just going to close that window, and we're right on day 22 here. 1 week for each model. It's just exercises created by AI, which has been good so far for me. So any of you that may be upper graduate PhD students or PhD, if you think there's something off in the way that we're learning with this AI generated lesson plan, please be sure to get a hold of me or post a comment or whatever. Okay, so here we go. Day 22, we're incorporating weather into our model like we did with Model 2. We also incorporated outside air temperature. Model 3 here, the missing link weather factor. Goal is to find weather factor used in Model 3. Just a note that I think these will get into a little bit, briefly get into what linear or matrix algebra is, and I'll just kind of fly over it at like a very high level. I think a whole college semester you would do matrix algebra, studying this stuff, linear algebra or whatever for engineers. So, but we'll just kind of look at it from a high level. Okay. Model 3 introduces a weather factor WF to capture combined effects of indoor temperature differences and outside air temperature. A common definition is weather factor equals temperature set point minus outside air temperature divided by 60, which scales the outside air influences to minutes. This is pretty similar to what we did with Model 2. Multiplying the delta temperature by the weather factor yields a feature that grows when outside air temperature is far from set point. Makes sense? This additional feature allows multiple regression to learn how weather amplifies or reduces warm-up time. Apply the concepts above using the formula or algorithm provided. Refer to mini examples below for demonstration. Okay, here we go. So this is our mini lesson for starting to study Model 3. Copy U. I just have this little math lesson script. See what it looks like. So Python math lesson. All right, see, what do we got here? Sometimes I like to just separate out some of this stuff. Okay, so this would be a temperature set point, like temperature set point for heat, degrees Fahrenheit, pretty common. 70 degrees. Looks like outside air temperature would be 30 degrees Fahrenheit. So weather factor would be temperature set point minus outside air temperature divided by 60. Guess they're coming up with that for their factor in minutes. Kind of interesting how they come up with this. The thought process is pretty cool, if you ask me. So our delta temperature, so this would be, we could even do something kind of fancy. So makes sense to me saying, like, I'm just going to say zone temp equals 62. This would be F. And then we could do temperature set point minus zone temp. Kind of helps me understand a little bit if I can put more information on here rather than just pure variables. But those variables come from something. Okay. So our weather factor for here is 0.67. Delta temperature times weather factor is 5.33. And I think that was supposed to be minutes or something. I can't remember. Well, I think we'll get into that. Why calculate weather factor for temperature set point equals calculate weather factor for 75 and 50. If weather factor is 0, does that imply that the outside, I'm going to say no for that. Okay, so our AI lesson plan says to do 75 and 50. Hold up a second. This is going to make sense. Oh yeah, so our temp set point. So this is our indoor temp set point. 75, 50. So it looks like our weather factor and our combined delta temperature times weather factor did change a little bit. So if weather factor is 0, does that imply, what does that imply about the outside air temperature? So if our weather factor computed to be 0, that would mean that these would equal out. So I think that would just mean that if the outside air temperature is really mild, usually 60 degrees outside. The building sits at, low 60s, almost 70 degrees Fahrenheit. The temperatures aren't going to drift much inside. So that would be, we don't need any outside air temperature adjustment factored in for optimal start. Why divide by 60? This was to do convert by 2 minutes somehow. I don't quite understand that. Maybe we can just ask ChatGPT. Okay, so I was asking it a little bit before this. So on the lesson 22 questions. Come on. ChatGPT is going really slow. So when weather factor was 0, that just meant that our outside air temp is very similar to indoor temp set point. And those conditions, we do not need more than likely optimal start at all. Optimal start weather factored into our equation. Also, the second question, to divide by 60, it is to create minutes, basically. Unit type. Please confirm. Maybe as that kind of sits and thinks, I'm almost kind of curious. So maybe look at. So we'll probably do this one. Maybe we could sneak this one in too. Looks like day 23, start to get into the alpha A, alpha B, alpha D parameters. Ooh, and it looks like our same other delta and weather factors, so we get into fancier math to predict minutes. Which looks kind of cool. I think like the model 1, we'll get into actually calculating these, which is really interesting to me to try and do that. But that's day 23. Okay, let's see. ChatGPT is done thinking. So question 1, if model weather factor equals 0, does it imply yes, your intuition correct? 0 means outer air is essentially neutral relative to building comfort. That makes sense. So weather factor means outside air is roughly similar, so we don't need to factor in. Okay, question 2. Ooh, not correct. Okay, we divide by 60. No, weather factor is not a time quantity, but 60 is not time conversion, so nothing about creates minutes. I love when AI corrects you. It even gives you a little smiley face. It's much more friendly than the real human on Stack Overflow or something like that. Minutes later come from regression, not weather factor. Okay, so what we divide by 60. Oh, 60 is degrees Fahrenheit. Got it. Okay, so that makes sense. So yeah, 60 is definitely a very neutral temperature. Got it. Okay, so dividing degrees Fahrenheit by degrees Fahrenheit removes the units, and then weather factor becomes a pure scaling factor. Okay, makes sense. Weather factor of 0 means we don't really need to factor in weather. Cool. So this is why AI is helpful and instantaneous, which I love, and friendly. Thank you, ChatGPT. Maybe we'll tell it thanks. Thanks, Chat GPT. You rock. Okay, so that is all I have for today, guys. Yeah, the human would never say this. No one on Stack Overflow or ping me anytime. Yeah, I see why people like AI so much, including myself, because they're nice. Dealing with real humans, they're more than likely not so nice. So, but you're lucky if you do get a nice one. So thank you, artificial intelligence. That's all I have for today, guys. Check back for tomorrow. We will do lesson 23. Have a great day.